Good morning, students. Welcome to the lecture 13 revision class of Design of Machine Members 1. So, in this lecture 13, we will discuss the balance unit of chapter 1, that is Introduction to Machine Design, the related stress problems. So, in the 12th lecture, we have given the introduction about the unit 1. In the 13th lecture, we will go about in details of the machine design concepts. Okay, right. We shall start the class. So we are continuing with the problems related to the basic introduction things. Okay, there is the tolerances and fits. Okay, so a composite bar made up of aluminum and steel is held between two supports as shown in the figure. So this is one support, this is one support, right? So here, uh, this is one steel bar, this is a aluminum bar. The bars are stress free at a temperature of 37 degrees centigrade. What will be the stress in the two bars when the temperature is 20 degrees centigrade? In that, find the supports are unyielding, the supports are yielding near the each other by 0.10 mm. So this is a 50 mm diameter steel rod, this is a 25 mm diameter steel rod with a length of 600 mm and 300 mm, right? So we have to find the supports are unyielding, the supports are yielding. Now the given data, right? Now take the change in the temperature. T is equals to T1 minus T2, that is 17 degrees centigrade. Next, the contraction in the steel bar. Contraction in the steel bar, that is alpha into L into T, that is 0.12 mm. Contraction in the aluminum bar, same formula, you will get the value. Then the total contraction is adding of both steel and aluminum bar, we are getting this one, right? Next, coming to the load force applied axially, right? So after the contraction, the length, this side and this side. So we have to find the cross-sectional area. A of steel is equals to pi by 4 d square. That is this one. For aluminum, this is this one. For elongation of the steel bar, this one is this one. Elongation. This is the formula. Okay. So this is the answer. Next, for the same aluminum bar, same elongation is equals to this one. Therefore, the total elongation is equals to delta L is equals to delta LS plus delta L A. Therefore, this is the value we are getting. Now find the stress in the steel bar and aluminum bar. So whenever the stress in the steel bar and aluminum bar taking with the supports of unyielding, the formula is this one. So therefore the pressure is this. Then the steel stress in the steel bar sigma S is equals to this one. Same the sigma stress in the aluminum bar is equals to this one. When the supports are yielding with 0.1 mm, consider with this so that you are getting the yielding of this one. Okay, so whatever the information you got, that is at 0.10 mm, the net contraction and the length is 0.2024 minus zero point 0.1, that is this one. Okay, in the same way the other problem is also we can do the same problem, right? So I will not discuss in detail. Okay, there's a copper bar, steel bar, these are placed at the same position which are inserted, okay, against other pipe. Same, the area you have to find, the area, you have to find the expansion process of the steel and the copper, right? And also finding the increase in the steel bar due to the force and increase in the steel bar due to the copper. Stress induced in the copper bar in the steel tubes of the pin, delta C is equals to P by A, delta S is equals to P by A. Therefore, induced stress in the pin stub is equals to P by 2AP. Now, next one is impact stress. Here, the machine members are subjected to load with impact. The stress produced in the member down due to the falling load is known as impact stress. Therefore, now considering a carrying of a load W at a weight H and falling on the collar provided at a lower end, let A is equal to cross section area of the bar, E is equal to Young's modulus, L is equal to length of the bar, delta L is equal to deformation, P is equal to force, sigma is equal to stress, H is equal to height, and the strain energy is equal to half P into pi L. So taking those into consideration, the potential energy lost by weight is equals to W into H plus delta L. Then taking the potential energy half P into delta L is equals to W plus, you have to take this one. Now, so by taking this one, just resolve it, half sigma into A into sigma L by E is equals to W of H plus. So into delta L, keep this value. So after substituting this one, we are getting this value. From this quadratic equation, we find sigma I is equals to W by A 1 plus sigma 1 plus root of 1 plus 2HAE by WL. Okay, next. So based on this formula, we'll derive a problem. The unknown weight falls through 10 mm on the collar rigidly attached at the lower end of the vertical bar, 3 meters and 600 mm into section. So take the value of E. If the maximum instantaneous extension is 2 mm, what is the stress on the value unknown? So write the given data. Okay. Now find stress as we have to find stress sigma. So we know that Young's modulus formula E is equal to stress by strain, that is delta L by sigma L by pi L. Therefore, sigma is equal to E into change in the length by L, that is this one. Now, value of unknown weight, let W is equals to this one, sigma is equals to the formula what you have derived in the just previous slide. So substituting all the values in this one. So after substituting these things, so making the squares on both sides, after substituting all the values, we are getting W is equals to this one. So like this, you have to find the unknown weight. Okay. Now, the next topic is resilience. Next topic is resilience. When a body is loaded within elastic limit, when a body is loaded within elastic limit, it changes its dimensions automatically, and on a removal of a load, again it regains its original dimension. So long as it remains loaded, it has to store some energy, right? On removing of the load, the energy is stored in the given off, as well as in the case of a spring. This energy, which is absorbed in the body when strained within elastic limit, is known as strain energy. Is known as strain energy. The strain energy is always capable of doing some work. Then the strain energy stored in the body due to the external loading within the elastic limit is known as resilience, and the maximum energy which can be stored in the body up to the elastic limit is called proof resilience. The proof resilience per volume of the material is known as modulus of resilience. Okay, so that's the concept of resilience. Now taking the formula, so the mathematically stored, that is the strain energy stored in the body is equals to U is equals to sigma square into V by 2E, and the modulus of resilience is equals to sigma square by 2E, where sigma is tensile or compressive stress, V is equals to volume, E is equals to Young's modulus. When the body is subjected to shear load, then tau square is equal to tau square by 2C, where tau is equal to shear stress, C is equals to modulus of rigidity. Therefore, the subjected to torsion, the value is 4C. Instead of 2C for a shear load, it is tau C for 4C for torsion load. Okay, next. So with this, we'll take a problem. A wrought iron bar of 50 mm in diameter, 2.5 mm long, transmits shock energy of 100 mm Newton per meter. The elongation, find the elongation and the stress, take E is equals to so this is a value. So maximum instantaneous stress, sigma is equals to maximum instantaneous stress. Therefore, the volume is equals to pi d square, pi by 4 d square into L. So this is the value. So we know that the shock or strain energy stored in the body U, that is equals to this formula. So substituting this formula, we will find sigma is equals to 90.3. Okay. Next, elongation produced. Elongation means the change in the length. Therefore, delta L is equal to elongation produced, we know that the longest length modulus E is equals to stress by strain. Therefore, delta L is equals to 1.13 mm. So next concept is preferred numbers. Preferred numbers. Next one is the preferred numbers. So when a machine is made in several sizes with different powers or capacities, it is necessary to decide what capacities will cover a certain range of efficiently within minimum number of sizes. It has been shown by experience that a certain range can be covered efficiently when it follows geometrical progression with a constant ratio. The preferred numbers are unconventionally rounded off values derived from the geometric series, including the integral powers of 10, having as a common ratio for the following factors. So here what's happening, what is the meaning of preferred numbers here? So the preferred numbers means whenever you are producing any uh, product, for example, take a motor, right? So we can produce zero point 0.5 HP motor, 1 HP motor, 1.5, 2 HP, 3 HP. So whenever you are producing with the different powers or capacities, it is very important to decide what capacities will cover the range of efficiently within a minimum number of size. This is given by the preferred numbers, right? Common ratios are this one. See these numbers. These are the common ratios. These ratios are approximately equal to 1.5, 1.26, 1.11, 1.06. The series of preferred and designated as R5, R10, R20 like that. These four series are called as basic series. The other series are called as derived series, multiplying and dividing the basic sizes of 10, 100,000 like this. Okay. So these are nothing but the preferred numbers. Next one is factor of safety. So what's the meaning of factor of safety here? So it is defined as the ratio of maximum stress to the working stress. Maximum stress to the whatever the stress you are working during the process, that is the ratio. Maximum stress to the working stress. Therefore, mathematically, FOS, factor of safety, is equal to maximum stress by working stress or design stress. In case of textile materials, example mild steel, where the yield point is clearly defined, the FOS is based upon the yield point stress. In such cases, FOS is equals to yield point stress by working or design stress. Okay, that is for the ductile materials. In case of brittle materials like cast iron, yield అనేది will not be defined for wet ductile materials. Therefore, FOS is equals to ultimate stress by working stress. This relation may be used for ductile materials. The above relations of FOS for static loading is this one. Okay, so this is the ratio for the this one. Which one? Ductile materials. This is the ratio for the FOS. Okay. Next one is design for strength and rigidity. In this design for strength and rigidity, all the concepts are discussed so far. The problems done for the strength based. There will be three permissible stresses or strength. Okay. So the design for rigidity or stiffness we will see now. It means the ability to resist the deformations under the action of external load. Okay. Along with the strength rigidity, it is very important operating property of many machine components. Example, helical and leaf springs, elastic elements in various instruments, shaft bearings, toothed bearings, worm gears, and so on. Forces subject the parts to elastic deformations. Shaft are bent and twisted, bolted, or stretched. Okay, so when the shaft is deflected, the journals are misaligned. Deflections and angles of the turn and shafts, where gears are fitted, cause the length of the teeth. With the deflection, the bearings cannot self-aligning takes place. Rigidity is particularly important. Product produced on the machine tools. Okay, so these are all the things, the most important design methods for increasing the rigidity of a machine elements. These are the points. One is to decrease in the arms of bending and twisting forces, the incorporation of additional supports, the application of cross sections, decrease of the length of the parts, etc. Next concept is torsional shear stress. Torsional shear stress. Okay. So what is the meaning of torsional shear stress here? So whenever the machine member is subjected to action of two equal and opposite couplings moment acting in a parallel planes, that is the torque or twisting moment, then the machine member is said to be subjected to torsion. Okay, the stress setup by torsion is known as torsional shear stress. It is zero at the centroidal axis and maximum at the surface. So if you take a example, consider a shaft fixed at one end and subject to torque T at the other end shown in the figure. So shown in the figure. Okay. Now, as a result of this torque, every cross section of the shaft is subjected to torsional shear stress. We have discussed about that torsional shear stress is zero. Okay, the maximum torsional shear stress at the outer surface from the following equation is this one. Tau by r is equals to T by J, that is equals to C into theta by L, where tau is equals to torsional shear stress, r is equal to radius of the shaft, T is equal to torque, J is equal to second moment, C is equal to modulus of rigidity, L is equal to length, theta is equals to angle of twist. Okay, so with this, if you see the shaft is subjected to stress, see here the length of the shaft, the twisting moment, the angle of twist. Okay, so here D is equals to 2R. Now, the above equation, right? The above equation is known as torsional equation. It is based upon some assumptions. What is this one? The material of the shaft is uniform. So, you should not have any changes in the dimensions, that is the diameter. The twist along the length of the shaft is uniform. The normal cross section of the shaft remains plane and circular after twist. All diameters of the normal cross section remains straight. The maximum shear stress induced in the twisting moment does not exceed the elastic value. These are the major things. Okay, so based upon all these things, this formula is known as torsional equation. So for the solid shaft, tau x by x is equal to tau by r. For a solid shaft of diameter t, the polar momentum of inertia is this one. Therefore, the torque T is equals to pi by 32 into tau into d4 into 2d, that is equal to pi by 16 tau dq. Okay, that is a torque formula for the solid shaft. For the hollow shaft with the external diameter d0 and d0 and di, that is pi by 16 tau into d0 cube minus 1 by k 4. Substituting k is equals to so on so value. Next, the expression C into J is called torsional rigidity. Therefore, the power P is equals to 2 pi nt by 60, that is equal to T into angular speed. Okay, so with this we'll do some problems. So at shaft transmitting so on so kilowatts with 160 rpm, 25%, stress is 70. Now take the given P value, N value, T max and tau. So T mean is equal to this one, T is equal to this one. The power transmitted, take the formula, P is equals to 2 pi nt by 60. So applying all this one, we'll get this one. T mean is equal to 100 by so on so, that is the value. And the maximum torque transmitted, T max is equals to so on so values. Okay, therefore T max torque is equals to 5 by 16, so on so 13.75 d cube is equals to, so on so value, finally D value is 81.5 mm. Next concept is bending stress. So ఇవన్నీ మీరు ఆల్రెడీ చదువుకుంటారు ఇంజనీరింగ్ మెకానిక్స్ సబ్జెక్ట్లో, రైట్? సో the machine parts of structural members may be subjected to static or dynamic loads causing the sections besides other types of stresses such as tensile stress, compressive stress, and shearing stress. So the figure shows all these types of stress. So I will not go in detail. Okay, the intersection of the neutral surface with any normal cross section of the beam is known as neutral axis. The stress distribution of the beam shown in the figure, the bending equation is given by m by I is equals to sigma y by y is equals to E by R, where m is equal to bending moment, sigma is equal to bending stress, I is equal to moment of inertia, y is equal to distance from neutral axis, E is equals to Young's modulus, R is equals to radius of curvature. From the above equation, we can say the bending stress sigma is equals to y into E by R. Okay. So also from the above equation, the bending stress sigma is equals to m by I into y. This is the ratio I by I is known as section modulus and is denoted by Z. The assumptions that are usually used for deriving the bending formula, assumptions, and these are the major types of assumptions. The material of the beam should obey the Hooke's law. The material of the beam is perfectly homogeneous. The material should be transverse sections. Okay, each layer of the beam is free. The Young's modulus is same. Okay, the loads are applied in the plane of bending. Now we'll see some problems based on this bending stress with this formula. So a beam of uniform rectangular cross section is fixed at one end and carries an electric motor weighing 400 newtons, distance of 300 mm. Find the maximum bending stress in the beam of 40 MPa. Find the depth and the width. The depth is twice that the width. So write the given data. So from the figure 5.7, let's find W, H, depth of beam, width of beam. The section modulus Z is equals to B into H square by 6. That is this one. Maximum bending moment M is equals to W into L, that is this one. We know that the bending stress sigma B is equals to M by Z with this formula. Okay, M by Z. Substituting these values, you are getting this formula. The breadth is equal to 16.5. Based upon the breadth, H is equals to 2 into P, that is 16.5. Okay, into 2, that is 33 mm. Next problem. Cast pulley remains 10 kilowatts at 400 rpm. The diameter of the pulley is 1.2 meter. So determine the dimensions of the arm having the bending stresses of 15 MPa. So write the given data. So torque is equal to T. The power transmitted by the pulley is equal to 2 pi n T by 60. Therefore, we are finding the torque value. Therefore, the torque transmitted is a product of tangential load and the radius of the pulley. Therefore, T by R is equals to 396.7 Newton. That is the tangential load. The pulley has 4 arms. Therefore, tangential load on each arm W is equals to 396.7 by 4. And the maximum bending moment on the arm M is equals to W into R, that is 99.2 into 600. So we find B and A value, major axis and minor axis. Section modulus for elliptical cross section Z is equals to pi by 4 A square B. So we are getting this one. Therefore, the bending stress is equals to M by Z, that is substitute the value Z is equals to pi B cube. So we are getting the B is equals to 10.8. Minor axis 2B is equals to this one. Major axis 2A is equals to this one. Next, principal stresses and principal planes. Okay, so the perpendicular planes which have no shear stress is known as principal planes, and the direct stress along these planes are known as principal stresses. Determination of principal stresses for a member subjected to biaxial stress. When a member is subjected to biaxial stress, then the normal and the shear stress are obtained like this. So we have to find, see here, the direct stress in two mutually perpendicular planes accompanied by the simple stress, direct stress in one plane accompanied by the simple shear stress. See here A, B, C, D. So here this one is moving in this direction, okay, in this direction, 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 and in this direction. Okay. So here we are taking the direct stress of one in a one plane. So moving this side or moving this side. Okay, moving this side or moving this side. So here what's happening? A rectangular body ABCD is uniform cross-section area. Thickness is subject to normal stress, sigma 1 sigma 2. In addition to those normal stresses, a shear stress tau acts also acts. It has been shown in the books of strength of material. Okay. Therefore, from the figure, we can say sigma T is equals to sigma 1 plus sigma 2 by 2 plus sigma 1 plus sigma 2 by 2 cos 2 theta plus pi tau sine theta. Okay. So we have to derive this thing so that we are getting the values. That is maximum stress tau T1, maximum normal stress tau T2, sigma T2. Therefore, the difference between the principal stresses T tau max is equals to sigma 1 minus sigma 2 by 2. This is the thing. Then applications where you are using this principal stresses. Okay. So maximum tensile stress is equal to this formula. Maximum compressive stress, this is a formula. Maximum shear stress, this is a formula. Where sigma T is the tensile stress due to the direct loading and bending. Sigma C is compressive stress. Tau is equals to shear stress. Next problem. It is subjected to a bending load of 3 kN, pure torque of 1000 Newton meter, and the axial pulling force of 15 kN. Calculate what? Calculate the stress A and B. So this is a bar. So diameter of the rod is 50 mm, length is 250, and having the pulling force of 15 kN. So write the given data. First find the area. Okay, then find the tensile stress, right? Bending moment at the point A and B, section modulus, and bending stress at A and B. Okay, so the bending stress is tensile at a point A and B. The resultant tensile stress at A is equals to this one, and the resultant compressive stress at B is equals to this one. Therefore, the stress at points A and B is equals to tau is equal to 16 T by pi d cube is a thing. Then stresses at point A is equals to this formula. Applying this formula, we are getting the values. Then the minimum principal stress at point A is equals to, apply this formula, we are getting this value. Then the minimum shear set at point A, tau A max is equals to this one. Then the stresses at point B is equals to sigma B by 2, that plus half is the formula. So you are getting this answer. Then the minimum stress at B, so apply this one, you are getting this. The maximum shear stress at a point B, okay, so you are getting this one. Next concept is the concept of stiffness in tension, bending, torsion, and combined situations. Stiffness in tension. So this is a object, force is moving this side. So the change in the length and the change in the area. So these are the values. Stiffness is bending, stiffness in torsion. This is a formula. Okay. So these things are already defined in the engineering mechanics. Combined situations, these are the formulas. Fracture toughness. It is an indication of the amount of stress required to propagate a pre-existing flaw. Very important material property. So see here mode 1. So it is having a flaw. So mode 2 and mode 3. Okay. So linear elastic fracture mechanics approaching the design critical components. Okay. So the following equation is this for fracture toughness. K1 is equal to sigma into root of pi A B. So this is a notation, right? So next one is the testing of the fracture toughness. I think you will not get an exam, but only for your understanding. Okay, so this is a B, KIC, and SY. Plane stress and torsional transitional stress states. Okay, so these are the formulas. So these are the notations. Okay, and this is a calculation of stress value. What is the meaning of orientation? The fracture toughness of materials commonly varies with the grain direction. Therefore, it is customary to specify specimen and crack orientations by the ordered pair of grain direction symbols. The first letter designates the grain direction normal to the crack plane. The second letter designates a grain direction like this, in which the three grain directions are designated as longitudinally, transversely, short surface. The six principal fracture parts are LT, LS, TL, TS, LS, and ST. So the movement, so this is a plate, the movement of this object moving in this direction, moving in this direction. See all the places of the positions of the object. Okay, so this is nothing but the orientation of the fracture toughness of the material. So with this, we have completed the unit 1 in all aspects. The lecture 12 and 13 related to the revision class of unit 1. So majorly you are getting some definitions in these problems and also the problems. I think you don't have any derivations. You will get the definitions and also the problems. Okay. So these are some of the problems what you are getting in this unit 1. So define the factor of safety, right? And what is the meaning of bending stress? For this bending stress, they may ask the derivation of the bending stress, right? So the derivation, consider a straight beam subjected to a bending moment. So you have to write this derivation. So they ask the assumptions. The assumptions are usually made while deriving the bending formula. You have to write these assumptions. Next, coming to the torsional shear stress. What is the meaning of torsional shear stress? How to derive it? Then you have to draw the figure of a shaft, and you have to write this one. And the assumptions made by this torsional equation is, these are the 5 assumptions. Next, how to design the strength and rigidity of an object. So this is a points where these are subjected to elastic deformations. Okay, then what's the meaning of factor of safety? What is the meaning of preferred? These are all the definitions where you will get for 2 marks questions in the part A and the problems in the part B. What is the meaning of resilience? Okay, the problems related to the stress. So these are all the various types of problems which we will get in the exam point of view. Okay, so the lectures 11 and 12 and 13 related to these things. So if you have any doubts, you can call me. Right, so this is only a orientation, this is only a revision class which is discussed in a very brief note. So generally it takes many classes only for your revision point of view. So what are the topics you will get, what is the syllabus content I have shown, and what are the questions you may get have discussed. Okay. So with this, we'll stop the class. With this, we'll stop the class here. So the lecture 14 will give the revision class on unit 2. Okay. Okay. So we'll stop the class here.